Hello everyone, Dr. Chen here. We're going to learn friction in this lecture video. And actually friction sometimes is very useful even if we don't realize that. For example, we hold the glass. We hold the glass cup and it's the friction that prevents the glass to drop to the ground. And if there's no friction, we cannot walk. We can only skate. We cannot walk, and it's friction that pushes us forward when we are walking. And this is what's going to happen walking on a slippery road with very small friction. Yeah. So actually, it's not only friction, not only that is a resistive force, sometimes is indispensable for us. In physics, we have two different types of friction. One is kinetic friction. Kinetic means there is a relative motion between two surfaces. And static friction means there is no relative motion. Now, if we look at this picture, we have the matchstick moving on the surface that's kinetic. Now, we try to push the car, but if the car didn't move, then the friction between the car and the ground is static because there is no relative motion between the tire, the surface of the tire, and the ground. Let's think about one question. When we are driving the car is rolling forward. The friction between the tire and the ground, basically the friction that pushes the car forward, is that static friction or kinetic friction? So let's reveal the answer at the end of this video. I will ask you to think about this. And static friction. Now, when we do static friction, we need to take into account the consideration of Newton's first law. Static means the object does not move. So the net force on this object is zero. Now we can apply different forces on the object, and the object still doesn't move. In this simple case, in the horizontal direction, there is only a pulling force and friction. So they have to add up to zero all the time, which means friction has to be always equal to the tension, the pulling force. So static friction can be a number that anywhere between 0 and the maximum value. And now if the pulling force is larger than this maximum value, then the block is going to start to move. So static friction can be anywhere between 0 and a maximum value. And this maximum value, we have a empirical equation for this. The maximum value should be a coefficient which only depends on the property of the two surfaces in contact. We call it coefficient of static friction times the normal force. So the larger the normal force, the larger the static friction can be. Now you can try to do this. If you have a book on the table, you try to pull this book. You probably would be able to pull this book. But if you apply a much heavier object on top of the book and then you try to push, you'll find out that the force required to move this book would be much larger. So it's related to the normal force between the two surfaces in contact. And this is not a vector relation. So if this is our table, this is our book, this is normal force perpendicular to the table, and the static friction is perpendicular to the surface. No, friction is parallel. The normal force is perpendicular to the table, and the friction is in parallel to the surface. So static friction and the normal force is perpendicular to each other. That's why this is not a vector equation, it's a scalar equation, only concerned about the magnitude of Fs is smaller than the coefficient of static friction times magnitude of normal force. And the same, we have an empirical equation for kinetic friction. Kinetic friction should always equals to coefficient of kinetic friction times m. Fk, now you see this is equal sign, but for static friction, this is smaller and equal sign. So it's kind of different. This is inequality. This is the equation. Kinetic friction always equals to mu k times m, but static friction can be any number between 0 and mu s times m. And what static friction does is to keep the net force on the surface to be 0. And if we go to microscopic scale, and the reason of friction is just because of the bumpy of the surface, and we will try to slide them, the bumpy on the surface will try to prevent the relative motion, and this friction force we experience. So now let's look at this very simple case. We have a crate, its weight is 500 Newton. So let's draw free body diagram. Weight is 500 Newton. And there is a pulling force T, F, S. So the maximum force to move it is 230 Newton. So we want to find out mu S. Of course, we need to use this. The maximum of static friction is mu S times n. We want to find out the mu S, so it's Fs maximal. Maximum value is 230, we already know, divided by n. So we need to figure out what is the normal force of this crate. And is static, right? So is moving is at rest, object is at rest, so the net force is 0. So in the y direction we have n subtract weight equals 0, so n equals weight, which is 500 Newton. The normal force is 500 Newton. Maximum of the static friction is 230 Newton. Normal force 500 Newton, so the coefficient of static friction is 0.46, and it doesn't have any unit. It's a coefficient without a unit. And then what is the coefficient of kinetic friction? Now we work it out. Normal force is 500 Newton. So moving at constant velocity, so net force in x direction is 0 to 0, so Fk equals tension equals 200 Newton. So we have Fk equals mu k n. Mu k is Fk over n. The coefficient of kinetic friction is 0.4 in this problem. Okay, now if we want to pull this box, is there any way we can apply force smaller than 200 and it will moving? So we need to build our free body diagram for this problem. What are the forces acting on the box? Free body diagram. We need to do free body diagram on the box. We should have normal force x, y, weight t. This is 30 degrees, and then Fk. So we want it to move at a constant rate. So the net force should be 0, which gives us net force in y direction is 0. And let's check what kind of equation it can give us. It would be in the y direction we have normal force, and then we also should have the y component of t. And the t, this tangent t this vector has an angle of 30 degrees, so its y component is 30 sine 30 degree. Subtract the weight equals 0. So we can find a way to express n in terms of weight and t. Okay, this is what we have in the y direction. And in the x direction, the net force should be 0, 2. And in the x direction, we have x component of t, and we have fk, which is in the negative x direction. And fk equals, okay, so we got an equation. We got a one equation, we got two equations. I think we can plug equation 1 to equation 2. So equation 2 is supposed to be t cosine 30 subtract fk, right? Fk is mu k, n should equal to 0. And then from equation 1 we find out n, normal force, actually should be weight subtract t sine 30 degree. And now we know all the numbers except the t, so we can solve for t, right? Cosine 30 degrees is 0.86 roughly. Mu k is 0.4. Weight is 500 Newton. T is something we want to solve. Sine 30 degree equals 25. Okay, put everything with t together. And then we can solve for t is 189. Actually, it's smaller than 200. So it's actually possible that we can pull this box with a force smaller than 200 if we cleverly apply the force a little bit above horizontal direction. Now let's move. Next example. So we have a block with mass is 2.5 kg resting on a ramp, and coefficient of static friction is 0.35. What's the maximum angle the ramp can have? That the block does not slide down. Maximum angle it has. And we need to build free body diagram. Let's choose x direction in this way, y direction in this way. So n is pointing in the positive y direction. So n has an angle 90 degree, and the static friction has pointing to the negative x direction. So its angle is 180 degree. And okay, mg pointing down. Those are three forces acting on the block. What's the angle of mg? We need to start from positive x direction and go counterclockwise. So it's actually 270 degree plus this angle. And using geometry, we can find out that this angle is theta, same as the angle of the inclined y. Because this angle at this angle gives us 90 degrees, this angle at this angle gives us 90 degrees, so they have to equal. So the angle of weight is 270 degrees plus theta. So what is x component of weight? Is mg cosine 270 degrees plus theta. And trigonometry will tell us this action is just mg sine theta. mgy, the y component of weight, mg sine 270 degrees plus theta. Okay. Trigonometry tells us is mg cosine theta. Now this got a lot of us confused. Why is the x component is mg sine theta and the y component is mg cosine theta? This is because theta is not the angle of mg. If we want to use the definition of vector mg cosine, we should use the angle of theta g. Let's say this one is angle of theta g. But theta g is 270 plus theta. The angle given in this problem, theta, is the angle of the incline. It's not the angle of the vector mg. We need to figure out what's the angle of the vector mg, which is 270 degrees plus angle of the incline. And so we always need to start from this definition of component of vector mg cosine theta g, and theta g is 270 degrees plus theta, and the trigonometry now tells us x component is mg sine theta. Remind ourselves, this theta is not the angle of mg, but it's the angle of the incline, and this angle can be any number, right? Okay, now we figured out what's the x component, what's the y component of the incline. Things become a little bit easier now. So in the y direction, net force should be 0. And in the y direction, we have normal force. In the y direction, we have normal force, N. And y component of mg, which is mg cosine theta, pointing in the negative y direction, should equal 0, which will give us n equals mg cosine theta. And now in the x direction, net force should be 0, 2, because the block should be at rest. So in the x direction, what do we have? We have the x component of mg, which is mg sine theta. Subtract fs is 0. But what is fs? Fs equals mu Sn. I already found out n. So it's mg sine theta subtract mu s n, right? And n is mg cosine theta. This is n. And now we can solve for mu s from this equation. Mu s is sine theta divided by cosine theta is tangent theta. So the maximum angle we can have is tangent inverse mu s. And mu s 0.35, so the angle is roughly 19 degrees. Okay. The last example. We have a block, 2.5 kilogram. Coefficient of kinetic friction is 0.35 now. This angle is 30 degrees. What's the acceleration of the block moving along the incline? Free body diagram. Normal force, mg. That's it. That's the only two forces acting on the block. No. Actually, we have friction, right? It says coefficient of kinetic friction is 0.35. So we have three forces acting on the block. Normal force, mg, and kinetic friction. Let's still build our x to be this way, y to be this way. Okay, this time I'll ask you to do the same thing. You will find out what's the x component of mg. X component of mg, n pointing to the positive y direction, fk pointing to the negative x. What's the x component of mg and what's the y component of mg? X component should be mg sine 30 degree. Y component of mg is mg cosine 30 degree. And in the y direction, net force is 0 because the block doesn't move in the y direction. We have n subtract mg cosine 30 degree equals 0, which gives us n equals 0.086 mg. Okay. And then in the x direction, we have net force does not necessarily equals 0 because the block is moving in the x direction may have acceleration. And the problem says we want us to find out this ax. So we need to find out the normal net force in x direction. What are the forces in the x direction? We have x component of mg, which is mg sine 30 degree, subtract fk, and this is just a 0.5 mg, and fk is mu k times n, mu k times n. This is n, right? Okay. So we need to calculate what's the net force in terms of g. So we have 0.5 subtract 0.35 times 0.86. It's roughly 0.3. So, okay. From here, we find out a acceleration is net force in x direction divided by the mass, and then we know net force is 0.2 mg now divided by n, so it is 0.2 g roughly 2 meters per second square.